All right, happy week 4, y'all. Glad you all are alive, so that's good news. So today we're going to talk about linear regression, so one of our second machine learning model. And a quick announcement, if you guys are all interested in the AI research, we have an AI research panel going on tomorrow from 6 to 7:30 at Franz Hall. It's a great way to meet professors, and they'll talk about any undergraduate research opportunities they have. And it's hosted by ACM AI Events. So definitely go check it out if you're interested in any sort of AI research or just like networking with other people that are interested in research. All right. Stay updated, stay connected with us. We have our Discord. That's where you're going to get all of our announcements. We also have an Instagram where we do post reminders about when we're hosting our workshops and upcoming events and stuff like that. Okay, cool. So today's agenda. So we are going to start off with a very fun example that we did in our workshops welcome day, very similar to that. Then we're going to go into understanding what a hypothesis function is. Then we get to do some very interesting math that Gregor will take over for. So partial derivatives, gradients, all that fun stuff. Then we get into loss functions, the core of optimization, as you'll learn about today. We have a small ethics portion. And then at the very end, we're going to go ahead and implement everything we learned today in Python. All right, cool. So we're going to go ahead and start off with the same scenario that we brought up. How will Joe Bruin do on his midterms? So the first thing we want to talk about are factors that will contribute to people performing on their midterms. So what sort of information do we need to know about the student to try and predict their score? And we call these information features of a model. So does anybody have any ideas? And they will most likely be the same ones as we discussed from Open Day. Workshops open day. Any ideas? What factor? Yeah, go ahead. How many hours of sleep? If you run on less hours of sleep, you are maybe more likely to do well if you're studying all night, or less likely to do well because you may not wake up in time. That is a fun fact that has actually happened to me. Yes. Your past exam scores. Any other ideas? Yeah. Hours of studying. So those are all good, really good ones. And I think almost all of those are on here. So hours of sleep, hours of studying, hours of lecture attended. Some may argue that this is less important than others, and past scores on homework. So all of these are features that we can then use to try and determine how a student will perform on their exam. And the score that they get on the exam is the target that we're trying to predict. So we use our features to then try and calculate a target. Any questions so far in this example on like what features are versus like what a target is? All right, cool. So right here, this would be like, let's say an example set of data. We have the average homework score that the student is getting, the amount of hours they're studying for, the amount of lecture they went to, and then their actual midterm percentage. So here, the first three columns are going to be our features that we are looking at, and the midterm percentage would be the target we are trying to predict. So right here, target is the midterm percentage, and we generally call this y. So if you remember y equals mx plus b, linear regression, linear equations, y is what we're trying to predict. And so y is the target. And now we can go into kind of formalizing this intuition. So we have a bunch of features, and we want to predict some output value y. Okay, so now the bottom part may look a little scary, but we'll get there. So when we were learning about like linear equations, we kind of say y equals f of x, where f of x equals mx plus b. And f of x here is what we call a hypothesis function. So a function that will take in our features and then output our predicted target. So we're making a hypothesis about what our target will actually be. So that is what the hypothesis function is, kind of in the name. All right. We call the predicted value from our hypothesis function y hat. So y hat is what we are predicting. Y is the true score. So for example, if somebody got a 90% on their midterm and instead we predicted an 85, y would be 90, y hat would be 85 in our case. All right. Then our input features are those columns we're talking about. And so if our target is y, we kind of go to the standard notation of our features being labeled as x1, x2 till xn. So if we have xn, we have n different features that we will be looking at to predict our y value. All right. So now onto these nice little row vectors and column vectors. So if you see x0 to xn, those are basically just our features. So in the example of hours of sleep, hours of studying, previous homework score. So we have three features and we would have three values, right? So for example, our column vector would be maybe you got 8 hours of sleep, you have a 95% average, and you've attended 0 hours of lecture. So that would be our column vector. Now, these thetas are what we call weights. And these weights are what we're trying to figure out. How important are each of these features in our model? So when you multiply all of this together, you will actually get theta 0 times x0 plus theta 1 times x1, so on and so on, theta n times xn. So this should remind you of that general linear form we have, y equals mx plus b. M is just, now we're calling it a weight. So how important is this feature to us? All right. Any questions about the notation covered so far? Right, cool. So now we get into the discussion of, are all of these factors equally important? So hours spent studying before your exam. How many of you think that's an important feature? All right, understandable. Number of previous classes you've taken. How important do we think that is to performing on an exam? Somewhat important, maybe not as important as, the amount of hours you spent studying. Number of pets you have. Very important, very important. Yes, thank you. Pets provide a lot of emotional support. Okay, and total amount of chocolate consumed, my personal favorite. Yeah, no, not as important as pets. Okay, understandable. But, we will have a different weighting for all of these values. And so in the previous slide, we were talking about those theta values. Those are the weights. So that is how we can indicate whether one feature is more or less important than a different feature. All right. So as we said, weights quantify how much a given feature impacts the final output. And our goal then will be to learn the importance of these weights. Which features are more important? Which features are less important? That is what we want to learn. So that way we can create the most accurate predictions. How is this learnable? This is learnable through a technique called gradient descent. And that is what Gregor will be talking about in a bit. And that is where all like the math and the derivatives and the fun stuff comes in. All right. And so we mentioned something briefly in like the course content called the loss function. And basically this loss function will be used to determine the accuracy of our linear model. So there are many ways we can do this, but the best way you can think about it is how far off is our actual predicted value from the true value, right? That gives us our error, and then we want to minimize that error across everything we have, right? So that way we're finding those optimal weights where we're not as wrong, basically. All right. So as a complete recap, we want to learn our hypothesis function. We want to learn the weights of our hypothesis function. So the function outputs the predicted target, y hat. We have a bunch of input features, x0 to xn, and our goal is to determine the optimal hypothesis function. And so right here, we have y hat of x is equal to b plus your standard linear equation format. And b is quite literally just like an intercept. It's like a bias is what we like to call it. It's something that we can just use to inflate things slightly. So for example, when you're studying for an exam, we may not have all of our features and their weights add up to like a 95%. We may say, on average, most people will get, if they do none of these, they'll get like a 50% on their exam. And then this is the remaining portion that we will use to determine the increase they'll get. So that is what that B value is. Any questions so far? All right, cool. So now we get into some more matrix notation. So this linear equation can be represented by the dot product of two matrices. And the dot product is basically x1 times w1 plus x2 times w2 plus ... plus xn times wn. So for conciseness, and so that we're not writing these really long column vectors and row vectors each time, you'll just say it as x times w, and that just means the dot product in this case. Okay. So once again, our model is xw plus a bias. And so that bias we will also be trying to optimize for. X is called our feature vectors because each of those values in there are features. And then the W's and the thetas are called weight vectors. That notation is interchangeable there. All right, any questions before we get into the math of it? Cool. Okay.
All right, quick question for everyone here. Who has done 31A? Okay, basically everyone. Anyone here done 31B? 32A? All right, cool. Quick review. We're going to talk about derivatives. As you all know, derivatives are the instantaneous rate of change of a function, essentially the slope at a point. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing, so on and so forth. Partial derivatives, for those of you who aren't in 32A, are essentially derivatives with respect to a specific variable. So in a multivariable function, such as 2x plus 3y squared, you will take the derivative with respect to x or y. So in this case, the derivative with respect to x would simply be the derivation of all the terms that involve x. So in this case, it's just 2. With respect to y, you're taking the derivative of 3y squared and just end up with 6y. Any questions on that? Make intuitive sense there? Cool. So just to cover a couple of concepts here, the gradient is essentially the vector of all of the different partial derivatives of a function in their corresponding vectors. So in this case, we have f of x, y, and z equal to x sine y plus 2z cubed. To find the gradient, we first take the partial derivative with respect to x, then y, and then z. And then we put them into a vector corresponding to their dimension within a vector. So in this case, a vector would be x, y, and z. And if there was 4 dimensions or so on, there would be 4 different spaces within the vector. So just quick review. What would the gradient of this function, x squared plus y squared plus z squared be? Is it A, the vector 2x, 2y, 2z? Is it B, 2x plus 2y plus 2z? Is it C, 1/3 of x cubed, y cubed, and z cubed? Or is it x squared, y squared, z in vector form? Who here thinks it's A? All right, good. That is the correct answer. And now we're going to talk a little bit about a loss function before we get into the math that we talked about so far. So essentially, we need to know how accurate we are in order to improve. You can't improve your score on a test without knowing what you messed up on the last one or how well you've done on the last couple of homeworks, right? So we need to find a way to score ourselves. The loss function is essentially our way of scoring ourselves. It measures the error in predictions compared to the actual ground truth values. An example that we'll be working with today is the mean squared error function. So you'd simply take the error, which is the term yi minus y hat I, where y hat I is the predicted value, and you square that. You sum it over all data points within the data set, and then you take the average. So you divide by the total number of examples within the data set. Does that make sense to everyone? Do you see where we're going with this? Cool. Really, the loss function will depend only on our predictions. And of course, our predictions depend entirely on the weights and biases that we have used in our model. Again, it can be thought of as a function of weights and biases within your model. And as we go forward, we will introduce some new notation to kind of reflect that. Time for derivation? So we're going to derive how we go through minimizing losing the loss by learning the weights in just a second. As we've kind of defined it so far, our loss is the function of weights and biases that scores our current variation of the model and its current configuration. We learn and improve by updating its weights and biases. If loss outputs a small value, our model is relatively accurate. We are essentially trying to find, either through a closed form solution or through a gradient descent approach, the weights for which our loss is minimized. And that leads us to gradient descent, which is what we'll be covering today. You can kind of imagine all of the loss functions that we're going to be working with in some form like this. These are actually taken from a machine learning course that is taught here, CSM 146. Highly recommend you take it. Essentially, what we're going to be doing with gradient descent is imagining the functions as a terrain and trying to find the lowest possible point of the function, and therefore minimize our loss function. In a single variable case, f of x is a one variable function, and f prime of x, the derivative, indicates whether the function is increasing or decreasing. And with that information, we can sort out where the global minimum is. I'm sure you've all done that in either AP Calculus or 31A or B. So if f prime of x is positive, we're going to be increasing. So f of x will grow as we move forward. We want to decrease f of x, so we decrease x and we subtract something from x. In this case, because it is single variable, we'll just be using the derivative. To minimize, we really just need to find the global minimum. Now, we can do that by finding the derivative and solving for the exact point, or we can do it algorithmically, which is what gradient descent is. In essence, rather than solving for a global minimum, we're going to take the point we're currently at, find the derivative at that point, and based on whether it is positive or negative, we will subtract or add something to x until we have reached a minimum value. So this formula here is the case of single variable gradient descent. So as I've just described, based on what we have for value of f of x and f prime of x, we're going to update x using a constant multiple times the derivative. Alpha is called the learning rate. We'll describe a little more why that's important later on. However, just for now, think of it as a scaling constant to make sure that we're not jumping around too far when we're taking these steps. In multivariable gradient descent, the gradient is the direction of the steepest ascent, and it depends on every single variable and essentially gives us what directions we need to move in each dimension to move towards a minimum. As we've kind of been describing, the goal is to decrease the value of the function, and we're just going to keep going the opposite direction of the gradient until we've found that minimal point. So for now, just to give us some real quick notation, x is now going to be a vector. Our gradient is the partial derivative with respect to each variable x. And as we've outlined, x will be updated based on alpha times the gradient f of x. And from here, we're going to really quickly derive the expression for the gradient of mean squared error. All right, can we see that? Perfect. All right, so up top, we have a little more extra notation. Right here, we have the definition of mean squared error. And we're going to find that as a function j. So as we know, each of these values, y hat and y, is a vector. And from here, we just need to calculate the gradient with respect to the vectors. So in our case, will be equal to the gradient with the derivative with respect to x of 1 over 2n of the mean squared error function. As you can kind of see, there's no real x term in this function, right? However, we just have to remember that y hat is a function of x, and then we can simply take the derivative of this function. So now that we have this expression, remembering that y and y hat are both vectors, where y hat is a function of x, we're left with a usable gradient, 1 over n times the summation over n of 2 y hat minus y times y hat prime. One moment, I'll get the slides back up. Sorry about this. All right, now that we've gone through the derivation, we're essentially just going to keep stepping down that gradient and calculate it at every point until we reach a global minimum. This is all kind of mathematically complicated, but in terms of conceptual thinking and your intuition, think of it as walking down a hill where the hill is represented by the loss function. So just to clarify here, there's a little bit of difference in notation. I used 1 over 2m in my definition of the loss function. It's really immaterial. It simply makes the gradient much nicer. Does anyone have any questions with how the derivation works out and what these formulas mean? Okay. Some of you have probably taken AP statistics and have heard about the line of best fit. Essentially, in the case of linear regression, when we complete gradient descent, we will find the line of best fit. This is a simple linear regression with one feature, trying to fit a line to an example data set. As we can see, that finds a line with a very good fit overall and a very low error with time. So in terms of testing our model, now that we have the method, we're going to first select some data points that we have that our model has not seen yet. This is a concept known as validation. We're essentially going to take a portion of our data set and save it and pretend that it's test data. We'll then feed the input of these data points into our model and hide the true Y values. Once our model has generated its predictions, we'll calculate the loss between our predictions and the true values. And that loss will tell us how well our model has performed. Here's just a quick link to a really good gradient descent visualizer. I'm going to leave this up for a minute if any of you are interested in looking at this. All right. We're going to take a quick break. The attendance code for this week is it's linear up in the corner there. Coming next, we're going to be doing a little lab and also discussing some of the ethics of linear regression and data privacy within AI.
Good.
Well, I will
Cool.
need your research.
Yeah. All right. I can present that.
We're ready to start again. Make sure to unmute.
Yeah, it's unmuted. Okay. All right, guys. Pretty good break. We're gonna end the meeting pretty short after this. Like, we're just gonna cover some ethics. We're gonna explore a little bit of code, and we're gonna call it a day. You know, we're not trying to like keep you hostage here, you know. So yeah. Let's talk ethics. You probably heard a lot of like talk about like all these like new innovations in machine learning and AI, and like how like sort of kind of like in this like little gray area. So like given that we've just given you like these very like powerful machine learning tools, I think it's important to like keep note of like I guess like things that can go wrong ethically in terms of like these techniques. So generally, in regards to this form of like gradient descent, linear optimizations and such, we run into a lot of ethical dilemmas in terms of data privacy. Because in order to develop really good models, right, you need to collect a lot of data. And normally the collection of that data or that storage of that data results in a lot of problems. More data, more problems. This is essentially the motto we're going with here, right? So a couple examples of that are these. So for instance, one example is data persistence. It's sort of like a two-way thing, right? Where let's say I collect data on a person, right? And that person dies, right? Am I allowed to keep that data? Like, or am I not, you know? That's one issue, right? Another issue, right, is you collect all this data and then you finish your study. Does that mean that that data is still usable for future research? Is that okay? Like if one person gives up their data for one certain research study, but their data is so important for another research study, can you just hand it off like that if they didn't necessarily consent? That's another issue there too. Another example can be seen in this idea of data repurposing, which I just like hashed over a little there, right? Where you collect one piece of data for one study, and then you just sort of use it in other studies without necessarily getting explicit consent from the original person who provided the data. And the last example can be seen in data spillovers, where where a study essentially just collects data from people who don't know that they're getting their data collected from. Maybe you're seeing a few parallels with certain large technology companies with this. We are an ACM AI club, so we're not going to be naming anyone, but, you know, just putting that on the table, you know. But one really good world example here, I know I just said like I'm not going to say any names, but let's drop a name. Clearview AI. How many of y'all have heard of Clearview AI? Can I get a raise of hands? Yeah, let's keep it like that. They're very questionable. So essentially, this AI company, they're based in the U.S. They decided to try to venture off into Canada and collect some data, specifically data of photos of people in Canada. And turns out the Canadian people they did not consent, and or they didn't consent to provide their data to this company, but this company just decided to ship off their data to the local police department so that the police department could use their data for whatever they wanted. That's not okay. I do not speak on behalf of ACM AI, but personally, like, that is not okay. And I sure hope that y'all think that that is not okay either, to be handing off your data to police departments without consent, or handing off data without consent in general. But yeah, wait, what?
Yeah. There's just one other really big example you guys may not know about. So how many of you use Netflix?
Wait, I can't. Come over near the mic.
Have used Netflix? Quite a few. All right. So Netflix has a bunch of recommendation systems, and they collect all of your data. And so their goal is they store everything on this really large matrix, and they're like, we want to predict what movie we should recommend you guys next. And so a bunch of Netflix engineers could not solve this issue. And so Netflix released a part of their database to the general public on Kaggle. They wiped personal information, names, all of that stuff you could think of. And they're like, hey, people of the world, figure out a great recommendation system for us. The prize was actually $1 million, and they hosted this recurringly for about 3 years. Now, the reason we bring this up in the ethics portion is somebody was able to identify the users based on the Netflix database. Like personal information was wiped clean from the data set that was given. And so the idea of data spillovers is actually a lot more prominent now because in the Netflix case, there's a website called IMDb where users leave their reviews and ratings and comments about movies. And turns out what somebody could actually do is they could cross-match the database Netflix had versus the IMDb database and identify exact locations of users. And so Netflix got filed for a lawsuit. That challenge has now been terminated. So any people who want to win $1 million, you got to find some different ways. But that is actually now a really big area of research in machine learning. How do we prevent, if we have one data set and another data set that we may have zero idea about what's in that data set, how do we prevent user information from leaking? If you're more interested in stuff like that, it's something called differential privacy, more specifically epsilon differential privacy, but just a nice tidbit on something maybe a little bit more technical.
Another fun little tidbit, whenever a company or any form of data collector or data broker says, we have removed personally identifying information, even without personally identifying information, you could be identified with as little as 14 factors about you. It was proven by a couple of researchers a few years back when they found a completely anonymous data set and managed to ID a couple of people from it just by looking at the data and checking through different places. So.
Yeah, so all in all, just be a little conscious about who you give your data to and what you use your data for. I know one of y'all watched all 16 seasons of Grey's Anatomy. I saw it on the data set. I know who you are. I'm not going to name you though, because like, again, we're trying to keep it ethical here, but I know. All right, but anyways, let's move on to the Python tutorial. We're going to be like analyzing code today. You're not going to be like writing it. But the link to it is going to be on here. I'll leave it up for like a couple seconds and I'll open it myself.
Over there.
Also, the link's over there. Thank you, Jordan. Yeah, let's pull it up here. Whoop. Oh, that is the end of the slides.
Yeah, the first thing you should do, make a duplicates of the code.
Indeed, indeed.
For you guys. If you want to modify it, that'll be the best thing to do. I don't think you can even run it if you don't really do it. So
Yeah, so should be one of the options on here. Whoop, whoop, whoop. Yeah, so this is the demo we're going to be working with. It's pretty much a skeleton. So what's up? Oh, full screen. Oh shoot.
people can see.
Oh, I see. My apology. Hey, I got some lovely images. Y'all close your eyes on those. Let me zoom in here. Oh wait, what's it?
Also make it light mode.
Light mode. I got you.
Yeah, there we go.
My apologies.
It will make you blind, but it makes it slightly easier to see for people. There we go.
All right. Can y'all see it in the back all right? Wonderful. Okay. Yeah, I'd recommend making a copy of this. But we're pretty much just going to do a quick walkthrough of like what's going on here. It's pretty straightforward. I know there's a bunch of like, you've seen like sklearn, a bunch of like random functions here. So all we're going to do right now is we're just going to sort of break it down line by line. And then after that, we'll call it a day. And yeah. Okay. So again and again, last meeting, we talked about how we're going to be coding in Python. This is Python code. So let's dive in. So essentially the essential libraries that we're going to be working with here is NumPy, sklearn. Sklearn is what we utilize to do linear regression with data. A lot of big words, don't worry about it. And matplotlib. This is just like a library that allows us to plot dots on a graph, which is pretty helpful in terms of trying to figure out like how effective our models are. We're going to see that in a little bit though. But essentially, how this skeleton works is, first things first, we're just, this is an example. We're not working with actual data, just to clarify that. And right here, all that these two lines are doing right here is we're beginning to set up our graph. So what our graph is going to consist of is we're going to have a bunch of random plot or random dots in between 0 and 50 on like our x-axis. And then we're going to take all of those dots from our x-axis, do a little bit of manipulation. As you can see on this line of code right here, we're going to add a little bit of randomness. We're going to map that onto the y graph. And then we're going to create a model to see if we can sort of apply linear regression to formalize what is exactly going on with the data, if that makes sense. So what this essentially is doing right here is, first things first, we're creating our x-axis right here. We're stating that the space, this lin space we're working with here, is between x0 to x50, and we're going to be working with num data, so like 300 data points right here. And then we're going to be adding an element of noise to our data, so just an element of randomness. So we just like create a couple random values with this line of code, not that complicated. And then all we're doing is our y-axis is just going to be all of our points on our x-axis. We're going to multiply it by 4. We're going to add 14 to it, right? So this is going to be our weights and all that fun jazz. And then we're just going to add our noise, so a little bit of randomness. So we got a bunch of scattered plots. And it'll make, so this is essentially what our graph is going to look like, just to clarify here. As you can see, it's not like a straight line. It looks like a straight line overall, but it's not a straight line. But after that inner code, we're going to perform this train test split function right here. Huge function. Don't stress about it though. Essentially, all this function is doing is it's helping us define 4 variables here, which is our training data for our x-axis and y-axis, and then the testing data for our x-axis and our y-axis. You're probably thinking like, what the heck does that mean? Essentially, out of our 300 points that we're putting on this graph, right? All that we're doing right here is that we're declaring that 0.2, so 20% of these 300 points on our graph, we're going to designate as our testing points. So specifically, in terms of our testing points, these are going to be our points that we say like this is going to be the behavior of our model. So the other 80%, that's going to be our quote unquote training data. We're going to test and see if those 80% of those points follows the pattern of our small 20% of our data. And then we also define this parameter called shuffle, and we set it to true. And all this essentially does is, if we did not define this, the 20% of data points that we would pick would be like first immediate 20% of points on the graph. We just want to randomly pick points across the graph so that our model is as it takes into account as many different like behaviors as possible, if that makes sense. So once we've defined our X training data, or our training data for our X and Y axis, and our testing data for our X and our Y axes, then all we're doing is we're calling this reshape method. Don't really worry too much about this reshaping method. We're working with a bunch of lists in Python, and certain methods require our lists to be certain sizes. So all we're doing is like, if we have like a size of like a 2D array, we're just shoving it into like a 1D array and stuff. Don't really worry too much about this function right here. But once we have our training data and our testing data, all that we're doing with these 2 lines of code right here is we are just simply plotting it on a graph. This is where that math plot library comes in here. And then, as you can see, this is what our graph looks like here. So, sorry. So as you can see, we have our testing data. Our red dots here, this is 20% of our 300 points that we put on this graph. And all of these blue dots here, as you can see, there's a lot more blue dots than red dots. That's the other 80% of our 300 points. And these points are what we're going to be using as training data in our model to essentially build a model that can apply linear regression and all that fun jazz. Was that making sense so far? Cool. If you have any questions, feel free to ask. I know it's a big room, but don't feel intimidated. I don't bite. But yeah. Anyways, so given that we have our training data and we have our testing data, now let's build our model. Woo! I'm not hearing the excitement, y'all. Woo! That's what we like to hear. All right. Okay, let's build our model now. So, lovely thing about Python is, wait, what? Yep.
I have a question. So,
Yep.
when you said like 20% of the data set, is that because of the consigned?
Yes, exactly. The 0.2 defines that we're designating 20%, so 0.2 is like 20 and whatever. 20% of our data is going to be testing, other 80 is training. Yeah.
I was like,
Yep.
on like the field dot scatter. Like, what is the meaning of like offline these things?
So basically, you see the dots on the graph, they're like semi-transparent, right? That's just defining like how transparent we want it to be. Like 0 is like solid, or I don't remember, but one of them solid is 0. and-
Zero transparent, one solid, I think.
Yeah, I think so. Yeah, it's just like how it doesn't affect the data. It's just how we plot it on the graph, how it looks. Yeah, you got it. Yeah. So, anyways, let's build our model. We're gonna have a lovely, fun time because we're working in Python, so you don't need to worry about like half of the BS that happens in Java or C++ or any other language really. All that we're doing right here is we're calling this function right here, linear regression, how convenient. And we're calling the fit method inside and applying our training data on both our X and our Y axis. So this is going to be our model. We're giving our training data as our input, because remember that models take input, they do a process, and then it throws out some output, right? So this is us putting in our input into the model, right? So now, given that we have inputted our stuff into our model, our model's done some fun jazz, and we ask our model essentially, what are our weights? What are our biases, right? What do these mean? So remember that the weights are essentially like tracking like how, if we manipulate our data a little bit, how does this affect the overall trend of our output? But a lot of big words. Essentially, remember that at the beginning of our code here, right, we're trying to compare our original X data to this Y data right here. And remember that we multiplied any given point in X by 4, and we added 14. So if you take a look at our weights and our bias right here, right, our weights, 3.95, right? Pretty close to 4, right? So our model's doing a pretty solid job here. So given that we've applied the same operation that drastically changes our data, that has effectively modified the general or average weight of the data that's outputted by our model. And then what about this plus 14 here, right? Regardless of how much we multiply our X by, it could be by like 100 or whatever, we still add that 14 to our data set. Where is that accounted for? Well, if we take a look at our model down here, it is projected here within our bias. So every time we input something into our model, we always add a very consistent value of 14 to it, right? So what the bias checks for is if our model outputs a very inconsistent like error within our data. So essentially what I'm trying to say here, right, is we input data and our model doesn't necessarily even trust our data, right? So that's what this bias means, is if it tracks that there's like inconsistencies within our data, it'll be accounted for within this bias. And we can tell that this is kind of working right now, right? Because our model bias is 14.12, whereas like this I guess like this extra little BS that we added was originally a 14. Again, it's not going to be perfect because we added this element of noise to it, this element of randomness, right? But it's pretty close, right? Normally, like you don't have the wonderful joys of like understanding all this data, but because we're creating all this data, we get the joys of like really understanding what's going on right here. But is that making sense to everyone or? Cool. Okay. So given that we know our weights and our biases now, normally like you can see your weights and biases and like you may just be sort of like, okay, like cool, but like does my model work, right? So what the fun thing we can do right here, right, is there's a convenient method here called score within sklearn, which essentially, given a model, we can just ask it, score it, right? And all it'll do is it'll give us a score. And we can't get a score over 1, but essentially 1 means we got like a perfect model. This is like exactly like what output we're looking for, right? And 0 just means like a horrible model. Like if you get a 0, just like stop trying. Like it's too far gone. But we got a 0.93 here, which means our model is pretty good, right? And you're probably thinking like, why is it a 9.3 and not a 1 if we created all this data? And that's because we added an element of noise, an element of randomness, right? So of course it's not going to be perfect, right? Anyways, so given that, we can calculate our mean squared error now, and we do that through these 2 functions right here. So this predict method right here, all that it's essentially doing is it is inputting our X test data into our model, and it's just storing whatever output it is in our Y prediction variable here. And then given that, we test our prediction data with our original testing data, because remember our testing data, we say that this is the behavior we want. So we have our prediction, right? This is our data that we inputted into our model, and then our model outputted something, and we're comparing that to like the real value that our model like has. So we're just double checking like how off we are. Oh, what? Did I break it? No, I did not. Hallelujah. So yeah. So this is our real data. This is what our model outputted. All we're doing is double checking how close we are to what our value is supposed to be. And so in regards to this data set in particular, it is 189. You're probably thinking, what the heck does that mean, right? So essentially, the goal of a mean squared error is, of course, we want an error of 0. That means our original data is the exact same as the data that is outputted by our model, right? But because we've inputted a bunch of noise, we've done a bunch of stuff to our data, of course, that's going to increase our chance of error. So you may be thinking like, what is a good range for error for a model? And the reality is it depends. It depends on what data you put in, how much noise is in the data, a lot of different factors, but generally the less error, the better your model is. Determining what's a good amount of error and what's bad is a whole different problem of its own. But anyways, given that we're almost done here, all we're doing now is, given all this data, we're just plotting it once again. So we're plotting our training data, we're plotting our testing data, we're reshaping and all that fun stuff. Anyways, graph, wonderful. So this is our original data here. We've switched the colors a little bit just to mix it up on you guys. But we have our training data, we have our testing data, and we have our line of best fit that our model has outputted. And as you can see, it generally seems to follow the trend of our data. And this is the idea of a linear regression. You got a bunch of different data, and you try to just output a very consistent trend across all of it. And that is an essential breakdown of the code. If you want to play around with it a little more on this Colab, if you made a copy of it, we got a little data set of diabetes values here. You can play around with it. This one has a bunch of different axes that you can play around with. You can like turn some on, turn some off, do whatever you want with your little fun diabetes data, but play around with it ethically. But yeah. Anyways, does anyone have any questions or anything? Cool. Anyways, that is going to be it for today's meeting then. Thank you all so much for coming. If you have any feedback or anything, feel free to fill out that form. Don't forget to declare your attendance if you want. But yeah, next week we're going to be covering logistic regression. And yeah, thank you for coming.